So we can start. All right. So hello, everyone. Thank you for joining our last NYU CUSP Spring Seminar. Today, we are very excited to host Dr. Ben Zaitchik, a professor in the Department of Earth and Planetary Sciences at Johns Hopkins University. Dr. Zaitchik is an earth scientist working on fundamental atmospheric and hydrological processes and applications to water resources, agriculture, and human health problems. Dr. Zaitchik leads multiple projects focused on the propagation of climate stresses through complex coupled natural human systems. Prior to joining Johns Hopkins University, Dr. Zaitchik was a research associate at NASA and an AAAS fellow at the US Department of State. He's currently the president of the GeoHealth section of the American Geophysical Union, chair of the World Meteorological Organization Research Board Task Team on COVID-19 and climate, meteorological, and environmental factors, and a commissioner on the City of Baltimore Sustainability Commission. Thank you, Dr. Zaitchik, for joining us today. Dr. Zaitchik will talk about urban heat, mapping, mitigation, and multi-objective planning. Let's give a warm round of applause to our speaker.
Thanks so much, Rampolos. And thank you all for the invitation to speak to you today. And I'll just say right now, please jump in as I go with any questions you have, or type them in the chat. If I don't notice in the chat, perhaps for Rampolos, you could let me know, just jump in if people have questions. So as Rampolos mentioned, I'm a professor in earth sciences. And so I approach the issue of climate stress very much from that perspective of understanding the climate dynamics. But more and more of my work in the recent years has been at that interface. So interdisciplinary collaborations, trying to think about how we can understand the propagation of these climate stressors. And so today I'm going to talk about some work we've done primarily in Baltimore, though we've worked in other cities as well, on the problem of urban heat. And I've opened here with an image. This is a thermal infrared image of the city of Baltimore. So what you're seeing here is the Chesapeake Bay, which is cooler. So I didn't put a legend here, but blue is cool, white is hot. And this is daytime emission, right? So more emission means higher land surface temperature. And so you can see the urban core stand out, which is a surprise to nobody, right? Because we all understand that we have this thing called the urban heat island phenomenon, where our cities tend to be warmer than the surroundings in most cases. And so, you know, as the climate science professor, I have to ask though, before we get into this, if you could just maybe type in the chat or unmute, whatever you want to do, why, in your understanding, are cities hotter than the surroundings? And I should say that there's almost no wrong answer. Maybe you'll surprise me with a wrong answer, but like there's like, you could almost anything you say will be right. So if people could maybe try to type in the chat, let me know why you think there's an urban heat island in general. Yeah, trees, cement asphalt cover. So yeah, thanks Akshay. So we're talking about green fraction, absolutely. We're talking about these built environment materials, right? Cement and asphalt. Thermal emissions from the structures, right? And that can be both because of their material properties or because direct anthropogenic heating, right? Yeah, so we've got a couple of good ones there. Yeah, and we could go on. There are a number of other reasons, right? And just before we get into this, I think it's important to think about that because there are going to be three claims essentially to motivate my talk today. The first is that the urban heat island seems so simple, but it actually isn't that well understood. And I don't want to overstate that. It's like we have some ideas, right? But understood process-wise enough to really inform targeted mitigation. It also really isn't that well measured, which is a little surprising, right? Because this is where everyone lives in the cities, right? So typically we think of data sparse environments as places of low population, but the urban heat island presents some real measurement challenges. And the final assertion, which I feel very strongly about, is that we haven't solved this in a way that meets community objectives. And again, that's a little bit surprising because the urban heat island, notwithstanding the fact that we don't fully understand or measure it, there are ways to solve this, right? And yet we haven't really done so. And so this is just quick to make sure that we're on the same page in terms of the causes of the urban heat island. I like this schematic from a paper about 10 years ago, which I was not involved in, but it's a nice summary. It basically says, why might we have an urban heat island? So number one here, the idea is that surfaces are dark, right? And so if you have dark building materials, they'll absorb a lot of light, solar energy. You also have multiple bounces. So even if your materials are not that dark, there's multiple opportunities for a photon to be absorbed. You also have pollution, right? And pollution plumes absorb and re-emit thermal radiation, kind of acting like clouds. You also have this issue of buildings trapping outgoing thermal radiation. So we sometimes talk about this being sky view for radiative cooling. And so it makes it harder to cool at night. You have direct emissions here, direct heat emissions as indicated here by the car. You also think of air conditioners, other engines running. You then have this idea that the materials, in addition to being dark, tend to be very thermally absorptive and retain the heat, which can lead to prolonged heating rather than rapid re-emission. Then here we've got our greenery, right, which people talk about, of course, if there aren't many trees, and so you have low evapotranspiration. What does that mean? It means you get more what we call sensible heat flux, as opposed to latent heat flux, which is evapotranspiration. And then you have ventilation effect. And there might be others as well, but these seven are kind of big ones. And what I'm going to note here is that if you then want to solve an urban heat island, understanding the relative influence of these seven would be very important, right? If you're in a situation where the evapotranspiration is very important, then a certain kind of green vegetation solution makes a lot of sense. If you're in a situation where actually ventilation is the most important thing, then planting trees may or may not help. So the first study I'm going to talk about today is a study that Tom Logan, a PhD student who's now a professor back home in New Zealand, did a couple of years back, which was to look at 4 cities across climate zones in the United States: Portland, Detroit, Baltimore, Phoenix, and looked at the land surface temperature. There's Landsat satellite data at daytime and nighttime to look at what might be some of the drivers of this remotely sensed urban heat island. And what Tom basically found was a few things. Okay, so what we're showing here is kind of a key result from his study, and these are data pooled across the 4 cities, multiple images for each city. And here I'm showing the daytime result. And what Tom did was he ran all these, different, regression and machine learning algorithms. But as you'll see, there might be some differences in the details, but in general, they line up pretty well. It doesn't matter what method you used, and even a relatively simple multivariate linear regression lines up in most cases. And so what do we see? Here we're seeing the change in the temperature relative to baseline. And here we see the sensitivity to the percent tree canopy and NDVI. That's a normalized difference vegetation index, so a satellite indicator of vegetation. In both cases, the more trees, the more vegetation, the cooler it is. Great, consistent with our understanding, right? Albedo also consistent with our understanding that as surfaces are brighter, it's cooler. And again, this is intra-urban, so it's across the 4 cities, but it's local, kind of 100-meter resolution gridded within the city. A digital surface model, such your elevation, right? So as you get higher up in elevation, it gets a little bit cooler. Again, that's consistent with what we'd expect. And then sky view factor, and what that means is that has to do with what the ability to emit heat. And we see here is that for the daytime temperatures, the more the sky you see, the hotter you are. So more sunlight getting in to the surface. Okay, so again, nothing too surprising here. And these are in rank order of importance, I should say also. So these are the 5 most important variables. Then you look at night. And at night, we see some very similar patterns of vegetation. Kind of interesting because when you think about it, evapotranspiration is a daytime phenomenon, right? So it's quite interesting that even at night, this vegetation is very important in terms of cooling. Albedo looks similar, and again, that'll be probably residual from the daytime, right? Because albedo is really just reflective of the solar radiation. One thing that's interesting is the sky view factor. Sky view factor flips, which again is entirely consistent with our understanding, right? During the daytime, the more sunlight coming in, the harder you get. At night, the harder it is for this thermal radiation to be re-emitted out of the urban canopy, the hotter you will be. And so sky view factor ends up being important at night. Okay, so a few points here. First of all, I opened this up by saying we don't understand the urban heat island that well, but obviously that's not entirely true. Like we and many others can identify these key factors, and you all type into the chat some of these answers, right? We kind of do, where you can describe it. That doesn't necessarily mean that we can predictively assess sensitivity to intervention. Another point here that we did this for 4 cities looking at interurban scales, but there have been other studies that have shown that even simpler models can work if you're looking at just the bulk urban heat island globally, like downtown versus the outskirts. You can do a pretty good job just using vegetation index and some indication of the population of the city can predict the magnitude of the urban heat island on average. Last point here is that I said that I'm showing you here day and night. So I bothered using a few of my precious seminar minutes to walk through the daytime and nighttime effects. Which brings me to the next question. You can type it in the chat an answer, which is the urban heat island larger during the day or at night? And you can't be wrong, which is interesting what your take on it is. You think that we have the city is hotter than the surrounding area in the daytime, or hotter than the surrounding area, or is the magnitude by which it is hotter bigger in the daytime than nighttime? Got a couple of night answers. Yeah, okay, got pretty good consensus for night of those who answered. Great. So we'll get to that. In fact, I would tend to agree with that, but it's a bit of a nuanced point, and here's why. If I look at data, and this is a study I didn't do, this is a study from Boston, but they had a nice graphic. And so what they're showing here is the urban heat island diurnal, so it's your average diurnal cycle of the urban heat island in 4 seasons: winter, summer, spring, and autumn. And what they're showing here is the urban core temperature versus suburban temperature, and they're showing the largest differential in the middle of the day, kind of noon into early afternoon. And so they're finding urban heat island largest in the daytime. And so why is that when you and we all just agree that's nighttime? Well, it's because this study, like the study that I just showed, is the surface urban heat island. Okay, they're using the satellite temperatures. And so here's what they were looking at. Okay, they were looking at satellite temperatures in Massachusetts. And what they show here is that, well, yeah, if they look at their satellite temperatures, show here in green, and then the red dots are another satellite giving snapshots, that temperature goes way up in the middle of the day. But they had one meteorological station they looked at in Boston, and you do not see that diurnal cycle in air temperature. Okay, so the satellite-derived land surface temperature, which is a radiometric temperature, right, is different from the air temperature. That you can call that technicality, but here's the issue: is that so many of our studies now use satellite data and define the urban heat island and other heat factors in terms of this radiometric land surface temperature, because you have this powerful gridded analyses at high resolution. It's much harder to get high resolution analysis of urban air temperature. And then when we come up with conclusions as to like, what is this urban heat island sensitive to, and what are the most vulnerable places, right? Or the most exposed places, I should say, to heat. Your answer could be wrong, right? Because you're basing that on a land surface temperature that at small scales does not correlate with the air temperature. And so we, like others, have tried to take this on by going out and measuring air temperature. And so this is, we worked with our local art college that helped us come up with a nice, elegant design that also maximizes airflow while minimizing light exposure. Put these little low-cost eye button temperature humidity sensors in them, and then put them out around the city in around 2-meter height, and just to measure the air temperature across different neighborhoods in Baltimore. And the way you end up doing this is just kind of like put them up in little trees. Usually you do put them in trees because what we've learned is that even with the shielding that we have, if you put these out on metal posts in bright sun, it's very hard to get an air temperature. That radiometric effect ends up getting you. And so we tended to try to put them in trees, but some of these would be isolated trees in settings that were mostly impervious. And when we do that, we can then start mapping out our temperatures, right? And so here's a map of Baltimore that we did, for example. This was for 1 year, average summertime temperature, or no, it's a snapshot temperature. Sorry, I'm showing here. The circles here are what we're getting for the maximum temperature from the eye buttons that we installed. And in the background here is showing your Landsat satellite land surface temperature snapshot. And what you'd see is that if you actually regress the scatters against each other, the correspondence isn't that great. There's some correspondence, there's some correlation, but there's a lot of small scale difference, as we might expect, because these variables are different. And we've done this, so personally, we've done this in a bunch of different places. We did Baltimore, but we also did Birmingham, Alabama, rural Alabama, Jersey City, Oxford, California, Nairobi, Kenya, Kampala, Uganda. So we've done this in a lot of different places, and you see something fairly similar, okay? And we're not the only ones. Lots of people are doing this, right? And so what do we find here if we now focus on the air temperature sensitivity? And so first of all, so I'm just showing you here, we both took the measurements, then we ran a WRF high resolution atmospheric model which we nested down 3 domains over Baltimore. And this is just an indication of the land cover according to that model's input. All right, and the little dots there where we place our sensors. And what do we find? We find what you all knew already. All right, that the urban heat island is greatest at night. All right, and so we're seeing here is this midnight through midday. What we're looking here is the difference in temperature for different land covers, as indicated here in these colors and these colors, right? Compared to the synoptic station. The synoptic station being your classic out in the field by the airport, which is where most of our synoptic, high grade WMO National Weather Service stations are. Okay, and so great. Maximum night disappears during the day. By midday, even in the densest urban environment shown by this red line, it's gone. And our model more or less catches that. The model had some trouble, with some of these intermediate land cover classes, but it more or less caught it to maybe not quite the magnitude, but certainly the timing when you compare the high intensity urban to the synoptic temperature.
Hi, Ben. Hi.
Yeah.
Sorry to interrupt. Hi, Rumi Chinar here, School of Global Public Health and Computer Science. Just some minor questions. So actually, if you go back a couple, maybe one slide or two, I'm just trying to remember. Previous. The one that had the hours of day and the air versus the Landsat. Yeah. Okay. So first of all, very cool work. Thank you for sharing everything. Yeah, I noticed here, it looks, so can you remind me what the GOES line is?
Yeah, sorry, I didn't say. So GOES is our geostationary satellite parked over the East Coast of the United States. So that's something that's gonna be giving you 30-minute data throughout the day of a land surface radiometric temperature.
So yeah, I was interested in the idea that the land measured temperature versus the air is different. That's a great point. I noticed here on this slide, during those nighttime hours, they kind of line up a little more closely. And I was wondering if that's, especially because of the finding that during the nighttime, the urban heat island is more predominant. I was just wondering how consistent that is, mostly from the perspective of someone, who's doing some heat, kind of heat event measurements from satellite derived measures.
Yeah, it's a really excellent point. And part of this is that the spatial structure of the satellite data gets much more smooth at night, which makes it more similar to the air temperature in general. And so, yeah, I'll be quite honest. I have not. Let me think of it. Have we done that comparison? I haven't done that comparison. And I'll tell you part of the reason why. And if you work in this area, high resolution thermal nighttime imagery has not been a thing until recently, right? Because you could do MODIS or GOES. Like the satellites you're using here, the MODIS data is 1 kilometer, the GOES is 4 kilometer resolution, right? For intra-urban studies, we're looking at hundreds of meters, right? And it wasn't until very recently that Landsat started releasing nighttime thermal data. And so I think you raise a really good point, and I would have to look it up to see how much closer your correspondence is if you just look at night. It's a really good point.
Sure, but good conversation. Start keep going.
Yeah, thanks for raising that. I'm definitely gonna look into that. Okay, so there we are. Okay, just to say that, so I just told you that the urban heat island is a maximum at night. Is that generalizable? I just showed you Baltimore. Here's a study our student Anna Scott did a few years back, and basically what you say is yeah, it's mostly true, but certainly not everywhere. So in more than 2/3 of the cities, we had 54 cities that we felt we could pair a reliable downtown station with a nearby synoptic station. And if it's pink or red, it means that the urban heat island is larger at night. So there's some places where it isn't, right? And they're kind of scattered about. It's not like you can say, oh, it's obviously the desert climate. It's well, no, it seems like, yes, some of the drier places are like that, but so is Buffalo, right? So there's some variability having to do with the urban form here. And these were pretty big data sets. And so it feels like these are real, right? And they probably have to do with exactly where the stations are sited and maybe some other details of the urban structure. But overall, yes, greatest at night. The other point that I want to make here, and I know this probably feels very in the weeds to those of you who don't think about climate monitoring a lot, but all of our understanding, just about all of it, right, of things like the urban heat island, involve a lot of people like me really focused on the city, right? And it's and then we find some baseline, oh, compared to outside the city, right? As if outside the city is all the same. what this ends up coming down to is that usually we use weather stations, right? And weather stations, there are very clear rules from the National Weather Service and the World Meteorological Organization that you put your station in a well-watered grass field, right, with no nearby obstructions. What that means is that you're comparing to a rural field. You're not comparing to like a rural forest. And one thing that we found interesting when we put all these I buttons out is that we also put some out in what we're calling our rural forest here, right? If you call the wood burbs rural. And what you see here is that if instead of comparing to our synoptic station at the weather station at the airport, we compare to a rural forest, we actually end up with a maximum urban heat island kind of early to mid evening, night after nightfall, which is kind of interesting, right? So you get a different answer, and the interesting thing to us is that that's our observation. The model caught it too, so there's no mystery physics going on here, but we don't think about that much. That the urban, this idea that we have the maximum urban heat island at night, which has some merits to it. It depends entirely on what your baseline is, and almost always our baseline is this idea of an open field, right? And why is that? Well, I think that's kind of interesting. It speaks to process here, about what processes might matter. So if this is where your typical rural weather station is, right, you have this beautiful sky view, right? If you're in a forest, your sky view is very much obstructed. And if you compare that to like a city, well, that's a big part of it, right? The urban canyon, your sky view is obstructed. And I think the fact that the nighttime urban heat island is much larger when compared to this rural site than when compared to this rural site, at least compared to the daytime differential between the places, is indicative of the fact that the sky view could be quite important. Right, that it's essentially hard for the forest to emit heat at night because you've got this canopy cover, and I'm assuming that your measurement is somewhere down here, right, at head height underneath the tree canopy. So that relates to the last subsection I want to do on this, like understand the urban heat island, which is the next question is like, how does the urban heat island change during heat waves? And so this is important, both, of course, because of the big health implication of heat waves. It also has direct implications for climate change, because one often does argue that heat extreme these days might be like your average temperature differential decades in the future. Okay, so yeah, into the chat. Please tell me, does the urban heat island get larger during heat waves, smaller during heat waves, doesn't change? What's your impression of this? And again, you can't be wrong. So just whatever you think. Anyone give this one a shot? There we go. Don't know. Smaller. Disparities overwhelmed with heat. Okay, so larger. All right, we got a smaller or larger, and I don't know. Great, I'll take it. So yeah, we didn't know either. So here is what we found. Forgive the scatter plots, please, but we need them. Okay, so what we're showing here is, first of all, we're plotting the temperature at a rural site versus the temperature at an urban site. Okay, and I'm just showing 3 indicative cities here to keep things simple. All right, 3 different kind of climate zones. And so every dot's a day. It's all summertime, June, July, August. Okay, and so one would think, so as temperatures get higher, if this slope is greater than 1, it means that urban temperatures are getting hotter faster than rural temperatures. If the slope is less than 1, it means that the rural temperatures are getting hotter faster, right? And what we see in these 3 cities, we have a beta term. This is a simple linear regression, obviously. 0.87, 0.83, 0.85. It's like, that kind of suggests that maybe things are the urban heat island is getting smaller, right? As things get hotter. And so then we go to our 54 city study, and what we find that, again, M here being the slope, right? The slope on that linear univariate regression is substantially less than 1, especially for nighttime. Daytime as well, but it's noisier, okay? It's not always less than 1, right? There's a good chunk, a solid minority of cities where it's larger than 1. But on the whole, the average is less than 1, and the majority of cities is less than 1. So that's interesting. And so then we said, the next was like, well, why? Like, why is the does it seem that this temperature differential is being smaller? Is it because of a difference in the urban site or the rural site? So then we said, well, let's say we take the average. So now my x-axis is the average temperature around the metropolitan area with as many stations as we could find, right? And then we said, well, how does our urban temperature change as a function of this average temperature? So if this slope is greater than 1, it means that the urban temperature is warming faster. Less than 1, it's warming more slowly, right? As temperatures increase. And it's like, almost exactly 1.0, right? So it seems that the urban areas is warming at the average. The rural site, however, is warming much faster than the average. So here again with the average temperature in the x-axis, but now it's the rural temperature, and these slopes are all greater than 1. All right. Okay, so it would appear that the urban heat island is getting smaller under hotter conditions, and that it is because not because the city is getting cooler, relatively speaking, it's because the rural area is getting hotter relative to the average. So why would that be? So then we say, well, maybe this has something to do with the prevailing weather conditions. And so we say, well, let's compare this effect under days that are a moist weather type. So weather type is a thing that we do as climate scientists, right? We're like, oh, is that a moist tropical weather air mass, or is it a dry Arctic air mass? You know, you just kind of like synoptically classify these things. So you say, well, what does it look like under moist conditions versus dry conditions? All right. And we see that the urban heat island here, the difference in temperature between urban and rural, is larger under dry conditions than moist conditions. So the urban heat island gets smaller when it's humid. And why is that? Well, if we look at this and look at the rural station versus the urban station differential in moist versus dry, we again get a slope much less than 1, indicating that's because of something that's happening at the rural site. Okay. And so what's happening is that the rural site heats up when it's humid. And it also just so happens that in many places, humid nights, especially, and I should say we're talking about heat waves defined by nighttime temperature here because of their health impact and the various reasons we've discussed. And so this idea that the nighttime heat island that a lot of people are concerned about for health gets smaller during heat waves seems to be related again to the sky view factor, right? Because during a humid night, which is more likely to be cloudy, right? And even if you don't have clouds, you have absorption and re-emission of thermal radiation in the planetary boundary layer, in that atmospheric layer near the surface. It's hard for radiation to get out, okay? During a clear, cool night, this is why the deserts are cold at night, or it's one of the reasons deserts are cold at night, or why the coldest nights we have are the clear nights in winter, right? It's because it's so easy to emit when it's clear. So on a humid night, this beautiful rural area with its sky view starts behaving a little bit more like the city, because in the city, it's always hard for the heat to escape. But in the countryside, it's easier in dry conditions than it is under humid conditions. All right, so the rural area heats up. So the baseline by which you're calculating that urban island is hotter. It's not the temperature in the city's lower, it's that the differential is smaller. Okay. Just there's a little bit of like, you know, urban micrometeorology for the semester. So it might not be what everyone here thinks about all the time, but I think these details really matter when we start thinking about what kinds of interventions might be most relevant, as well as when we think about vulnerability patterns. Okay. So very briefly, in the interest of time, I think I've already kind of hinted at why measurement would matter so much and why the current measurements are limited. And partly it's because these beautiful satellite images that we depend on so much are not measuring the same phenomenon as the air temperature, let alone the heat index, right? When you bring in humidity to the question, which I just don't have time to get into today, that matters for our heat impacts, right? So having satellite data is fantastic, but it's not a substitute. But there's been good work done on this. So in the past 5 years or so, NOAA, the Climate Program Office at NOAA, working with the National Integrated Heat Health Information System, or NIHIS, have had this urban heat island mapping campaign. And so they've been going out to cities around the country in collaboration with the community, and they run transit. They have car-mounted temperature and humidity sensors, and they'll run daytime, afternoon, morning, afternoon, evening transits across the city to try to characterize spatial variability in air temperature and humidity. And these are all public data, and they're doing more every year. So this inventory is really growing. And then you got people like us, and again, it's people like us, not just us. There are a number of groups out there that are doing these kind of in situ stationary measurements, right? Saying, well, let's just leave our measurements out over time in the city to see how things change with time. And we were able, Ray Shee, a PhD student here, was able to do a really detailed quantitative comparison, because we have both for Baltimore. So the lines here are the transits the NOAA team ran. The dots are I-button sensors. And we were able to compare them, look at how they do for spatial temporal inference. This paper that I'm referencing here gets into those details. And basically what we found is that there are some advantages to the stationary network. First of all, your measurements aren't only on a road, right? You can access other land cover types. Secondly, you catch differences between weather types, right? It's not just a quick one-day transit, you're doing it constant monitoring. On the other hand, the transits do have some advantages, right? It's quick in, out, easy. You can use higher quality equipment because it's not going to get stolen and because you're using it for different cities every week. So, and you get big spatial coverage. So there's advantages to both. And we currently have a project with the NOAA office that runs these transits to try to figure out the optimal combination. It looks like it's probably doing the transits and then having, maybe 10 or 12 stationary sensors in addition. Okay. So now I want to use the remaining time to talk about something that that I think, based on my reading, you guys have a very diverse institute there at CUSP, but I think that this is maybe a little closer to the way that some folks are spending their work hours, which is thinking about how do we use this information in combination with other sources of information to try to meet community objectives. Okay. And so what do I mean by that? Okay, so there are some really strong design visions for solving urban heat island. Okay, this is one that was put together. It's actually, I think, a good example of collaborative design, but still it's a figment in someone's imagination right now of what a particularly underserved area in Baltimore might look like with a lot more targeted green infrastructure intervention, right? But there are a few issues here, right? So the design vision is there, but it's pretty rare. Again, this one's an exception, but they usually are designed with community consensus. Very often they kind of come in from either the government or the designer level, right? And they often don't have a benefit cost quantification that can support decision-making under resource constraints, right? So they end up being, I don't want to say luxury projects, but they end up being driven sometimes by happenstance, right? Where do you have the right motivated people at the right time to make something happen? And hey, that's how change happens, right? So that's great when you have motivated people making things happen. But if you're in a situation where you actually want to treat this as one of your priority climate change adaptation responses, and you want to reach places where people may be not entirely engaged right now, it really helps to have the benefit cost analysis to understand how to allocate your resources. So we have been working with the city of Baltimore and communities in Baltimore on an effort to design equity-oriented community heat reduction interventions. And to do that, you need to start with what are the objectives of the community. Okay, so first thing we try to do is measure exposure. Okay, and so to do that, that's a lot of what I just spent most of my time talking to you about, like how do you really measure heat? Okay, but then also you need to figure out what the metrics are that matter here. So that means not just like, are you doing daily or nightly temperature, heat index, or wet bulb globe temperature, or like all these other different nerdy things we do as climate scientists, but also indoor versus outdoor, right? How does the exposure map onto vulnerability and behavior patterns, right? So that requires some collaboration. Then what you need to do is look at the mitigation options. And I'm not going to have time to talk about this today, but there's a literature growing on this, though it still needs a lot of work, right? Which is understanding your opportunities and constraints. So it's going to be social and economic constraints, certainly, but also what is the effectiveness of decision interventions. And so there have been interesting papers to say, well, like, what percent tree cover do you need for the trees to actually be effective at cooling, right? Is one tree enough? Do you need like a forest, right? And so being able to do that means that you need to quantify the efficacy of the different mitigation efforts. And then what we're doing is we're taking information on both of those and putting it into a tool called the City Heat Equity Adaptation Tool, City Heat, that allows for participatory definition of scenarios. And then it's a simulation and optimization tool that provides some potential outcomes that you then work with communities to kind of iterate on what kinds of plans make the most sense. Let me describe that in a little bit of technical detail. And then delve into a case study. And so the basic motivation is this: that if you want to develop adaptive strategies that integrate both temperature and exposure reduction actions to mitigate, we're going to focus on health here, so to mitigate heat health risks, you have to deal with decisions that happen over time, right? Some of these things take decades to take effect. So you're talking about like days to decades timescales, and space, right? So you might have sub-regions within a city like neighborhoods. So you have a space-time problem. And there are huge uncertainties inherent in the problem having to do with the climate trajectory, having to do with the effectiveness of the intervention, et cetera. And so what City Heat does is the decision analysis tool that simultaneously evaluates different actions and optimizes multiple objectives. It does that while considering various future scenarios, all right? And the outcome then is to generate these adaptive strategies at fine temporal and spatial scales. And so, which I'll give you an example of in a second. But the way this works is that city heat's got to do two things, right? It has to be a simulation model to evaluate the effects and costs of alternative heat adaptation plans. And it also has to have an optimization component. And we do a many objective optimization approach because some of these factors cannot be compared one-to-one. And so it does a search for the non-dominated or Pareto optimal plans that meet various objectives. Okay. We do that for those who think about the technical elements of this. It does this with a direct policy search method, so that in each year, we go by year, you can do it by whatever time interval you want. You use system information from previous time steps to guide the decision at later time steps. And so that means that when you make a decision, it depends on the scenario, right? It also depends on the most recent system information, and also depends on any decisions you made up to that point. And we use the direct policy search method here for computational efficiency. It allows us to constrain a problem that might, if we want to simulate 20 years, but we only have a 3-parameter function to relate the decision, then we save a lot, right? And so city heat here, and I'm going to show you an example. We're calling it city heat because the first application was to heat in Baltimore. We hope that's going to be a generalizable tool to support not just urban heat adaptation, but other objectives. We're currently expanding it to look at issues related to flooding and heat, and hopefully can expand even further beyond that to look at other ways that we can use this as a participatory, or I should say, a tool within a participatory platform to work with communities on solutions. All right, that was a lot of technical background. The papers in prep, we can talk about in the Q&A if people are into the technical elements of this. And again, this is Ray Shi, that PhD student who's the real expert on this. So I'll answer what I can, but he's the one who built it. And I want to talk, I'm going to use the last few minutes I have here to talk about the Baltimore case study for city heat. And so to talk about the Baltimore case study, you need to know a little bit about Baltimore, all right? And so in Baltimore, there's a phenomenon that if the dark joke is this, that no matter what you map, it looks like this. Okay, when you can be mapping poverty, you can be mapping crime, you can be mapping race, you can be mapping, in this case, childhood asthma, right? And you always end up with this pattern on the east and the west, all right? And this is known as, the term that's been coined as the black butterfly. So Baltimore has a black butterfly geography in which this butterfly shape indicates where you have a lot of your challenges when it comes to various social factors, and also where the challenges and opportunities may lie in terms of reducing vulnerability to heat and other climate vulnerabilities. And so I just put that out there because if you think about this, I think it's indicative of many American cities, right, or cities in general. Baltimore is perhaps an extreme case, being a hyper-segregated Rust Belt city, but it's this idea that you're going to have this geographic separation, right? That you have a spatial element that you should be thinking about, that includes difference in demographics and socioeconomics and vulnerability and in opportunities that need to be considered by any optimization model attempting to inform adaptation. The other thing I should say about Baltimore is that there's a lot of work going on to reduce the urban heat island. It's a priority. And so I just this picture out of the window of our public health school building, a lot of white roofs going in. We could talk at length about the white roof rationale. There's also things like greening plans being divided with communities. So we work with the Broadway East community. They have this green print where right now they are very low vegetation cover environment, but there are opportunities that the community supports to try to change that. And there's also a study that came out a year ago, which was pretty interesting, a little less than a year ago, by the Smart Surfaces Coalition that just happened to choose Baltimore as its case study, trying to do a benefit cost analysis of various cooling efforts, cool pavements, white roofs, green roofs, things like that. And so we have the foundation of a cost benefit analysis, though we could talk about that. We think there's a lot more work to be done on it. We have the engagement and will to do something to reduce heat. It's been viewed as the top risk in the city's disaster preparedness plans for a number of years now. And we also have this geography of inequity. Okay. So when we take city heat into this case study, it was really designed for this case study. The first time we did this, we're now working at higher spatial resolution, but I'm showing you results from the study that divided the city into fairly large units, but at least captured, the black butterfly would be these neighborhoods and these neighborhoods over here. Okay. so we can distinguish between the general vulnerability patterns. We want to understand heat in the context of climate change. And in the city, that's a complicated thing. So the way we start off doing that is by looking at an ensemble of projections, all right? And so these were drawn from the Cordex ensemble, for those familiar with it. So those are dynamically downscaled global climate models with regional models, and then we can bias correct them and look at projections for the city. We did not attempt to model the urban heat island other than as a static phenomenon right now. Okay, so we can adjust, we kind of take this as a synoptic temperature, and then we can just do an offset for the urban heat island. We're not taking advantage yet of some of those details that we've worked on that I presented earlier. And then what do you do? Well, then you sit down with some of your partners in the city and the government and the communities and say, okay, well, what are the community's objectives here? And so that we end up defining to say, like, okay, well, let's say we have a scenario family where our policy goal is, for example, to reduce racial inequities and heat-related mortality, because right now we have horrific inequities in heat-related mortality. And so then we say, okay, well, what are the target objectives within that? Well, we maybe want to maximize total mortality reduction in the city. We may also want to minimize the possibility of a disaster, right? Like a heat wave that kills a lot of people. And we also might, sorry, that was the bottom one. And we also, the middle one, we want to minimize the mortality rate difference by race, right? So that's kind of an equity-oriented objective. Meanwhile, we probably want to minimize the cost, and maybe we want to go for some carbon reduction here, right? So we can have these additional objectives. You then have scenarios that capture your uncertainty, okay, or your modeling decision related to things like discount rates, or your uncertainty in the projected climate conditions, for example. And then you have some, parameters you put in here. And then we test heat information by saying, oh, okay, first of all, as I said, we'll start with a spatially uniform temperature. And then we say, well, what happens as we get more information about the urban heat island into this? That's still ongoing work, so I can't present that to you today, but I'll show you how the system basically works. And so keeping my eye on time here, so I might have to go a little quickly through these last couple, but please ask questions when we get to the question and answer point. Here's your parallel coordinate plot. Well, what this shows is you want to be down at the bottom of this plot is optimal. But you can't be optimal for all of your objectives in this many objective optimization at once, right? These are different Pareto solutions. So these are plans, 166 Pareto optimal plans, okay? Some of them are very cheap, but they don't save a lot of lives. Some of them are very expensive, and they do save a lot of lives, right? And then you can look at these objectives and talk about the benefits. You can also do things like this, say, okay, well, what is the cost to mortality reduction relationship, right, among these Pareto optimal plans? We can also say, well, what's the trade-off between total mortality reduction and mortality rate difference in that equity question, right? And so, for example, and the colors here are again showing costs. So you can, for the same mortality reduction here, here's plan 65, the numbers are arbitrary, and plan 60. 60 is a lot cheaper. It's green, this is orange, but orange is much more effective at reducing inequity. Here, what you do is you concentrate all your investments in the places with low relatively lower vulnerability, so you can save lives quicker. It's harder to save lives in some places. And just to look at one plan here, the last thing that I'll have time to show you is plan 6 happens to be the most expensive but most life-saving plan. And so then you can do something like go in here and say, well, what did that look like? What happened in plan 6, right? And so we can say, okay, across the different areas, how over a 20-year period, how many trees did we plant? What did that mean for the tree canopy? How much cool pavement did we install? How many cool roofs do we put in? I'm not showing you, but you can also look at like the deployment of cooling centers. And then oh yeah, here's cooling centers. So you can look at over time, again, 20 years here for our different neighborhoods. Where do we put our cooling centers? Where do we plant our trees, and when and where do we put in the cool pavements and cool roofs? And you see a lot of the investments are front loaded because then you get the longer benefit, right? But these are the tools that we then bring back to the city and the community and say, okay, well, what do we need to invest in, right? What is the community saying? Tell us this looks right to us, or versus no, we are not interested in that for our community. And that will then we update our constraints, right? And update our priorities and try to figure out whether one of the plans that came out of that simulation makes sense, or whether we need to go back to the drawing board to find something that makes sense and meets the budget constraints of the city. So I'm gonna end there. I just want to say, like, what I've tried to describe today is a little bit, again, and sorry if I went a little more into the climate physics than people are always interested in, but I think it's important to understand these details of the phenomenon that we just kind of take for granted, but actually needs to be understood better, how we're trying to measure it, and also some of the efforts we might be able to make collectively across disciplines and across in a transdisciplinary way with communities and city officials to meet some needs when it comes to reducing the urban heat island or climate change. I think we have a few minutes for questions, so I'll stop there.
Thank you, Dr. Zaitchik. Let's give a warm round of applause to our speaker today. Thank you for your presentation. Lots of insights, and the chat is already very active, so we can start with that. And I apologize in advance if I mispronounce names. The first one, feel free to jump in, to unmute yourselves and jump in. The first one is from Akshay Deverakonda. This presentation is really informative and thought-provoking. Given the disparities between air measurement and remote sensing, can there be a role in satellite imagery / data in thermal sensing, or will air measurement always be the gold standard?
Yeah, and it looks like Costas jumped in with a good answer already, which is that, yeah, the land surface temperature is a really important driver of fluxes, right? And so you really do want to know that, right? And it's very important for that as an input to understanding the system, certainly. So I think it's not going anywhere. In a way, it's the gold standard for that. Air temperature is this, composite result of many processes. So it's definitely real there. I would also say that, we come to this question of thermal comfort. And so air temperature, we go to so much trouble to make sure we're measuring just the air temperature just right. But that's not the only thing that makes you feel hot. Like if you are next to a brick surface that's radiating at you, that matters. So radiant temperature is a thing that people are looking at for its direct health impacts. And so in that sense, the land surface temperature is actually indicative of that radiative component. So there's a lot of role for land surface temperature to play.
Thank you. So we can open it up to the audience. You can raise your hands and then we can go in that order. Just to iterate the comment that is in the chat by Dr. Cartalis, land surface temperature as deducted from satellites is an important parameter for urban, among other studies, in terms of surface, atmosphere interactions, including the transfer of heat from the ground to the overlying air sensible heat. At least it depends on the urban fabric, the surface materials, and urban form, the latter in terms of the sky view factor. Okay, we have a couple more questions from Chen Yu Yan. In the multi-objective work, is it true that you have to build a faithful simulator? Could you tell more about the simulator or how to build a simulator that could simulate the time horizon to many years?
Yeah, it's an interesting question, right? I mean, if you're smart in the way you frame your question, then the fidelity of the simulator probably falls by the wayside. I will say it's the optimization that kills you in terms of CPU or GPU, right? So like the simulator is not limiting for us. And we went to 20 years, so that was a reasonable planning horizon. We could do a lot longer. So the simulation does not limit that. In terms of what the simulator doing right now, honestly, it's using a lot of functions from the literature, right, to understand what the change in different impacts might be associated with different interventions, as well as the heat health link. So we're drawing from Roger Pang's Medicare-based study right now for mortality relationships. So there's, right now we're kind of depending on a lot of that. So the simulator is pretty simple in its own right. And to your question, like, does that matter, right? Like we're prioritizing making that simulation more accurate. But I suppose depending on how you want to think about that participatory decision process, you might be able to get away with a fair degree of simplification. But yeah, it's not time horizon. That was just our choice. We stopped it for 20 years, but certainly not because the simulator was limiting.
And the question from Joe Beaufort, re-intervention. Are there examples of using city government regulatory functions to scale up use of, quote, light surfaces, not only on government budget?
Wow, thank you. I could talk your ear off about this. I've become kind of a crazy person about this issue, right? Because we should. And so here are ways that it's being done. And so the last phrase, not only on government budget. Well, let me talk about the way government budget can be used, okay? So New York City, you guys are way ahead of the curve, right? Like you guys are doing really well on light surfaces. And where did the biggest infusion of cash for that come from? Crime reduction, right? So the jujitsu there, or the real truth, I suppose, right, is to put it in the crime budget, because if it's more comfortable inside your home on a hot night, you're less likely to be out wandering the streets. is the thinking. And so they're funding not under some kind of climate adaptation or health budget, they're funding it under the crime budget. And you know what, their budgets to fight crime is considerably larger than our budgets to fight climate change or to improve the health of our citizenry. So so that was a clever legislative move. In Baltimore, we recently had a city council member introduce basically just a regulation, right? Saying like, when you replace your roof, it must be above a certain brightness, right? So like, and the fact is that's cost neutral in almost all cases. Like, so really, I think, and we're seeing that adoption happen because it's cost neutral. Roofers are getting educated to recommend this to their clients because it's not going to cost them anymore. The problem is that people who proactively replaces their roof, right? Like, so it's a slow turnover time, right? Because, you know, I'm a homeowner. I have never thought, gee, this is what I want to spend my money on right now. And so speeding that up is tricky. Now we talk about getting beyond the government budget, right? So my thinking on this, and interested in your thought at this point, this is my layman's thinking, right? I really I'm trying to work with the energy company, right? Because when's the peak power demand? The peak power demand is during hot afternoons and evenings, right? And so to what extent is the power company designing its fleet to meet power demand during those times? It is, right? And so if that's how you're designing your fleet, if you can reduce power consumption during those peak heat hours, I would have to think, and I haven't done the analysis yet, but I'd love it if someone would. There's got to be a reason. There's got to be a huge financial incentive there for the power companies, especially in decoupling and decoupled systems, right? To reduce people's cooling energy use by basically going out themselves and painting the roofs white, right? Like, I would think that the electricity providers would be strongly incentivized to do that if they thought it through. And I haven't talked to the right person yet, and it's also not quite my field, so I need to talk to people who really understand how this works. But I think there's an opportunity there, and that's where I see the strongest non-government funding opportunity right now. But I'm sure others have other creative ideas about it.
I don't know if there are more questions. If people want to unmute themselves, there is one more question in the chat. Okay, so for our last question, do you collaborate with other researchers to look at how land temperatures, urban heat island effects may influence the spread of infectious diseases, e.g. malaria, dengue, etc.? Is this a possible future direction?
Yeah, absolutely.
Yeah,
thanks, Akshay. So I will say most of the infectious disease work that I do is not explicitly urban. So we do a lot of temperature-based prediction using satellite temperatures or modeled air temperatures, right? For especially, as you note, the vector-borne diseases, right? So we do that a lot for malaria or waterborne diseases like cholera. Did it for COVID. Don't get me started. I could have given a talk about that. That's a messy one, but it's the one that probably might be the most useful for that we're working on is dengue, right? Which I think you listed there, yeah. And that's because, as I think the question implies, right? That's where you've got your Aedes mosquitoes, and they're urban mosquitoes, and dengue is an urban disease, right? And so we are doing a fair bit of work in. Another thing about Aedes, right, is that they're city mosquitoes and they live in things like empty tires and flower pots, right? They don't live in natural puddles, and so that means that their breeding habitat is very much sensitive to the radiative environment. All right, so how much energy is coming into that container of water. And so people have developed these, Aedes breeding habitat energy balance models that we then use in some of our work, where we take some of our climate analysis, including urban heat island effects, right, and say, well, how is that going to affect the temperature, right, and evaporation rate off of these potential Aedes breeding sites, and also the development rate of Aedes, which is also temperature sensitive, right? So it can be really useful input there. And so, yes, it's absolutely a direction for future research. In terms of, okay, you phrase as land temperatures, urban heat island effects. Yeah, so still in all, the air temperature, I think, is we tend to focus on the air temperature and the incoming radiation. We aren't literally using the satellite land surface temperature right now, but that's just us. I think that it's a close enough, the variable is closely related enough that one could probably make use of that if you had the right resolution.
Thank you, Dr. Zaitchik. Before we end, before we finish, feel free to raise your hand, but before we finish today's session, I would really like to thank the people who have been in the background for all this time during the spring seminar. our great administrators, Kimberly Reed and Allison Bradley. I think Allison is in the room. Feel free to open your camera. Thank you so much for helping us throughout the seminar. Thank you, Allison. Yeah, today's the last one. I do hope we have you on the next seminar. I don't know if you want to be, but I would really like that. Okay, so I don't know if there are more questions for our speaker. All right, thank you, Dr. Zaitchik. Thank you for joining us today. Thank you, everyone, for joining. Let's give a warm round of applause to our speaker. I hope the end of the semester finds everyone not too stressed, and hope to see you in the fall seminar series. Goodbye, everyone.
Thanks, everyone.